Today we're going to look at in-situ particle size distribution testing using Cascade Impactors. It's a long-established air measurements protocol, and that is not as widely used, but it can provide us with some really good information about the operation of air pollution control equipment and processes and their size distribution. So let's first look at a definition of what is a cascade impactor. As you can see from the screen, it's an air measurement device, and what it does is it divides the particulate matter in the gas stream into different sizes. It pulls the select sample stream into it and then breaks it apart through a cascade of nozzles, and the nozzles are progressively finer, hence it sizes smaller and smaller matter. And there's an impaction surface below each jet, and as some particles hit the surface, others continue on through. So that's basically what a cascade impactor is by definition. Just to give you some idea of its history, notice the first one was developed in 1860, right at the beginning of the Civil War, so it's been around a while. The important dates here is that as we go down, if you look down here at the very bottom into 1970, and we have 1970 basically because that's when impactors really kind of reached a maturity. And so what we do today is not very different from what was done in 1970. I'll point out to you on the left there, under theories, it says Marple 1970, and on the right it says Pilot UW for University of Washington Stack Impactor 1970, both significant developments at that time. This is what a cascade impactor looks like. This is a University of Washington Mark III. This is a 7-stage impactor, and you can see the flow lines by going by the definition of how it proceeds to move down through the impactor. It is accelerating, it is taking out smaller and smaller particles. If you look at the picture, you can see in the upper stage the large holes, the large 6 holes in the top, and as you move down through, you see the holes getting successively smaller till the last stage, where the diameter of a hole in this last stage is 0.01 inches. This right here in the upper right of the picture is the backup filter, 47 millimeter quartz fiber glass filter like is used in EPA method 17 that catches any particles that have escaped. On these are the collection substrates called donuts, and they take a substrate that collects the particles. This is the University of Washington Mark V. It's the impactor most used for research. You notice it's an 11-stage impactor. There's Dr. Michael Pilot from the University of Washington. All the impactors originally called Pilot University of Washington Mark V's because it was too hard to list the names of all his graduate students who actually did the work developing these on the impactor. So it became called the Pilot University of Washington Mark V. You see here spread out a Mark V with the additional stages. Those white donuts are the ultra pure quartz fiber substrates. They're mounted in very light stainless steel foils, so your tare weights and your final weights are not as heavy as you might think they would be. Why would you use an impactor? There's a valid question. So they're used mostly to understand usually how existing air pollution control equipment is working. If the process changes, we want to know how that affects the existing equipment. Suddenly, if your air emissions go up because you made a process change, something obviously changed. So we do a lot of diagnostic work. In the past decade or so, we've started doing more droplet, actual wet sampling. We'll get into that later. I've done sampling where we've looked at product loss. They were losing stuff out the stack, and they wanted to look at could they put on another piece of control equipment that would stop that. In 1990, the California Air Resources Board asked Southern Research Institute and EPA to promulgate a test method to use cascade impactors as an actual official sampling device, and they did that. So CARB 501 is actually sampling a stack for particulate matter using a Cascade Impactor because they wanted to look at ultrafine particle emissions, and they also wanted to have some idea of what a plume would look like coming from a device several kilometers downwind. Here's basically the physics in a picture. You see, you saw those holes. This is a close-up of a single hole in a jet. I call it the dead man's curve effect because if you put yourself in the place of one of these particles and you're speeding down a road and suddenly you come across the curve, at the moment you start to turn the wheel, you have that moment where you don't know whether you're going to go through the guardrail, which is this particle down here, or you're going to successfully make the turn and continue on down the road. So the physics and momentum of it play in that way. So each of those individual holes, this is what's happening in there, in each hole, as it moves successively down through the impactor. Really brief math. Don't want to, bring too much math into it, but basically we have this thing called a dimensionless inertial size parameter, which is psi, PSI, the Greek psi. And as you see, it's just a function of a lot of the different things, the diameter, the jet, the gas, the density of the particle. So we need some way to predict so that the data has meaning. So that's what this does. At first, people weren't sure whether there was a large application for this. And so if you remember the timeline, the gentleman on the left was Marple. This is Dr. Virgil Marple in 1970. In his PhD dissertation, he basically was able to show that impaction parameter constant can be used over a very wide range of flows and temperatures, which makes it so you don't have to have a graduate level research project every time you go out to take a sample. There is a set of equations that govern how it works effectively. And so what we end up with when we're talking about particle sizing, we talk about D50s, diameter of the particle at 50% collection. You see those same parameters here. What that means visually, when you have a sample that's collected, ideally only one size would actually be collected, but in the real world that's impossible. So what we have is this S-shaped collection where at 50% collection efficiency, this is the size. We have higher collection efficiency of larger particles, which makes sense, and we have lower collection efficiency of smaller, which also makes sense. So ideally, a lot of the large particles have already been collected at stages above this particular stage we're looking at. If you plot that D50 plot for a 7-stage Mark V, you have flow rate across the bottom. Here's 1 CFMs right here. So you see we operate these things down in the 0.3 to 0.5 flow rate. And then each stage, here's the corresponding stages, number of holes and size of holes. And then so if we were running at, let's say we were running at 0.3 of a CFM, as we're going up, we could go here and go across, and this would tell us what size particle would be removed on that stage. So here's the, let's look at a picture of how you would do the sampling. So originally when they first started sampling, you notice that the impactors had straight nozzles. And so you hear what you see, you see what most of you are familiar with as like an EPA Method 5 train with impingers and vacuum pumps and dry gas meters, pretty standard. But here's an impactor, a Mark III on the end of it. You notice because of the straight nozzle, you have to put it in and turn it down. Well, certainly any of you who are watching this who've done stack sampling are thinking, yeah, if that's a foot long and it's only 3 inches, how am I supposed to get that in and around and turn? The impactor itself is 2.875 inches in diameter, so it fits in a 3-inch port, but obviously making that 90-degree bend to get it facing down, it would be a very difficult application. So how did we solve this? So what happened is, as you see on the next slide, is that the EPA talked with Southern Research again while they were working on the California Air Resources Board method and said, we need to be able to sample at right angles, just like regular stack sampling. So EPA and Southern Research Institute, led by Dr. Joe McCain, one of the world's leading experts in particle sizing, and I'm happy to say my mentor over the years, developed a peak pre-cutter that goes on the inlet to the impactor. It enables us to sample at right angles to the gas stream, but also know a size cut, a D50. This particular head here, by the stack conditions, it has a specific D50. PCSC is Pollution Control Systems Corporation. That was the corporation developed by Dr. Pilot of the University of Washington to actually sell the University of Washington Cascade Impactors. So as like most very niche industries, everyone knows everyone and everyone's tied together. So if we look at the picture now of how the impactor would sample, it is in a more traditional perpendicular. You can stick it in. You don't have to, if this is narrow here, if this is long here, you know, it's okay. You can still get it in. Again, it fits in a 3-inch ID port. 4 is better, but it will fit in a clean 3-inch ID port. So let's start looking a little bit more here. Here is a picture of a Mark V that has been used on a combustion source. I like combustion sources. You can see why I like combustion sources, because of the carbon in the samples. They make a very nice black sample. You're sampling a source with white particulate when you first pull the impactor apart and you see nothing, you know, it kind of gives you pause. So here we are. This is right behind where the pre-cutter is, and you can see the patterns of increasingly finer, smaller particulate working its way down through. And here's the backup filter, again, a 47 millimeter ultra pure quartz. You figure these particles that are here, the D50 of this stage is probably 0.2 microns. So whatever's gotten through, you notice it's like just a staining on the filter. So this is a ultrafine fume of particles that is being captured in this backup filter, to give you an idea how small this is. So let's look at some examples of sampling and what you can get out of this, because this is the important thing. So one of the basic ways of reducing data is we take the data, whether it's 7 for the Mark III, or usually what I use is the 11 Mark V. We nowadays put it in a computer, we do a spline fit, and you get this fit with all these data points. So this is a log across the bottom of the aerodynamic diameter and the cumulative percentage. So this gives you a feeling of its distribution. An important parameter right here is the MMD, the mass mean diameter. And if you go to the 50% and you move across where it intersects right here and go down, that's about roughly 2.5 microns. So what that tells you, in this particular gas stream, the particle size distribution, half of it is larger than 2.5 microns, half of it is smaller than 2.5 microns. So that's very useful. The next graph is one that gives you real, gives you visual import about the nature of how the particles are generated. This is what we call a DMD log D, the difference in mass with respect to the log of the diameter. Again, we have diameter across the bottom and a logarithmic. And up here we have concentration based on how much was collected on each stage. What you see right here is these are called modes. And so most emissions are a bimodal distribution. They have 2 distinct formation mechanisms. This one happens to have 3. You notice we have a hump here at about 20-25 microns. This comes from the pre-cutter. This is material that was probably mechanically generated, maybe by crushing, or could even be the size of the original particles. So it hasn't undergone a lot of physical change. And as we move down, we see this large peak here, right around a micron in size. This is a process generated like combustion. These are combustion products. They could be some other chemical reaction, but they're usually significantly different than the material here in the original. And then when we come down to the small peak here, you see we're down at 1/10 of a micron. This is usually vapor phase condensation, where a gas, and when it reaches a certain temperature, it precipitates right out of formation and forms usually submicron tiny spheroidal particles. So that's a classic trimodal distribution. By looking at this right away, you can see there's a lot of material here that's a micron in size. And if I need to lower my emissions, I need to really damp down this peak. So let's look at some processes next. What we're looking here is a process time-dependent comparison. So this is a combustion process. So what we did was we said, okay, let's go ahead and look at it from the inception of the combustion for the first 3 minutes. You see the purple run 1. And so you see that familiar hump right there, greater than 10 microns, followed by 1 around a micron, similar to the previous one. So the large peak on the right is material that's, you'd probably classify it as char. So it's just beginning to catch fire. It may be pieces that are breaking off that still retain the nature of the original product. Whereas the peak to the left, around a micron, that is material that has combusted, and now we have more carbon. The volatile materials have been burned off. So after we did that sample, we said, okay, let's see how thorough this combustion is. So they did another burn in this trial facility. We waited 3 minutes, and then we started the process. And you can see from the green trace how everything shifted down as we talked about. So now we have a trimodal distribution where there's very little larger size char left. We have a good amount of combustible material in the middle, combustion products, but now we have vapor phase condensation. It's very hot in the chamber. We have gases that are being driven off, and as they reach downstream in the duct where we're sampling, they've condensed into submicron particles. As you can see, that has a size of less than 1/10 of a micron. So that's a pretty dramatic look at the progression of a process from its, especially a combustion process, from its incipient firing through a more robust, mature burn. In the next one, something that we do a lot is we take microscopic pictures. A lot of times people want to understand what is the nature of the particles. Is it a group of small particles that are all agglomerated together that are moving through the gas stream and acting like a large particle, or are they individual large particles? This is a classic picture of heavy fuel oil that's burned extensively in the Middle East. And what heavy fuel oil, when it's combusted, it makes what are called centispheres, which are, as you can see, they're hollow spheres. So even though they're larger and they're spheroidal, but they're hollow, so they're less dense than you would think they are looking at them. But that's a classic heavy fuel oil particle. Next, we'll look at what happens if we analyze those substrates. So if you think back to the shot of each individual substrate that had those deposits on it, we can take that ultra pure quartz substrate out, submit it to a lab. In this case, we can have it digested and do a regular metals analysis on it with atomic absorption or ICP-MS, as this is. And you can see what we did here is we took it and went ahead and broke it down into the particle size distribution by metal. So we have boron, chromium, iron, and nickel. And so, as we would expect, the metals showed up in a very similar pattern, overlaid to one another. But what you see the difference is the magnitude of the metals form. And again, talking about our vapor phase condensation, take note of where this peak falls. It's slightly less than 0.2 microns. And unfortunately for this particular client, it's 0.2 microns of chromium. So you put those two things together and you have a source that is very difficult to clean and presents a significant health hazard. So this was a tough project for the client to figure out how to deal with this. Looking at the next slide, we can see We can do XRD, X-ray diffraction, where instead of looking at individual elements, we can go ahead and try to identify the compound that's in it. You notice here the standard issue where the sodium represents albite, the magnesium represents magnesium oxide. In this case, we were doing droplet sampling downstream of a scrubber demister, and they wanted to understand whether the gypsum that is formed in the scrubber was being thrown into the stack gas, and what they were measuring in their increasing stack emissions was indeed gypsum that should not have been in the gas stream. So we looked at some substrates and analyzed them for individual compounds, and when you put it together, you can say, yeah, yes, that's gypsum. So I've kind of had a teaser as we've talked about, gone through here about wet gas streams. Any of you sampled know that if you look at EPA 201A for PM10 and PM2.5, it says thou shalt not sample a gas stream where droplets are present. Well, never being one to take being told what I can't do, we went ahead and worked on, could we go ahead and sample droplets and get the combination of both droplets and particles. So to be able to do this, you need to ask yourself the question, do we want to understand what's happening in the duct directly downstream of a scrubber demister? In other words, droplet carryover. Are we trying to understand the droplets that have entrained particulate that should be coming out in the sump of the scrubber? Are they being thrown into the gas stream and erroneously being counted against the source as emissions? So that's one issue you need. And the other is, or do we want to understand, as we mentioned before, what does the plume from the stack look like several kilometers downwind when it's dried out and there's no more water, and any particles that have been released from any drops, or if there was any nucleation and we had particle growth. So when it hits an ambient air station, or whether a school or whatever's downwind, what's that going to look like? So we need to answer the question, because there's two different approaches to sampling. So if you look at this picture, you will see a pre-cutter on a University of Washington Mark V. We were evaluating the operation of scrubber demisters. It was a very large duct. It was horizontal. So because it was horizontal, we did not want to run the impactor upside down as we're collecting wet samples. So we created this being able to turn it so it sits up straight. Luckily, they had 6-inch test ports, and we're able to drop it down through. And so, but the real trick to here is when we zoom in on the pre-cutter in the next slide, you'll see that there is this PCSC modified pre-cutter. It actually accepts an ultra-pure quartz liner. And what this liner does, as the drops come in most normal impactors, they would hit a stainless steel surface, hard surface, and they could shatter. And if they shatter, they could create smaller drops that could then be entrained lower down in the impactor, flood the impactor. What the liner does is it acts like a blotter. Anybody who still uses ink pens, you know what happens when you have to use a blotter after you write. So that's what this does. As soon as the drop touches that fibrous surface, it is wicks right out of the gas stream, and along with its particulate matter that's entrained within the drop, it's captured here, while the rest of the gas then, without the large flooding drops, can go down into the impactor and do a size distribution. The next picture is this liner after it's been used, and I think you can see fairly dramatically that this dark splot right here is the particles that were inside the water drops that should have come out in the scrubber demister, but instead were moving along in the gas stream and carrying this extra particulate matter with it into it. So this had a cut size of about approximately 9 microns. So the D50, so most of the large drops, which are 50, 100 microns in size, would all come out here. But you can see the amount of particulate matter. Graphically on the next slide, you can see what we did was, so After we did the sampling, we took the impactor to the lab, took it apart, pulled the substrates out, and weighed them wet. So the wet weights constitute both water droplets and particulate matter. So if you look at the pink or fuchsia or magenta or whichever color this looks to you, with the large peak, again, our large peak at the 20 microns, that's the water drops plus that dark spot of particulate matter. But then as you move down to size, you see we have another significant peak at about 0.3, 0.4 microns. That's the solid particles that are too small to be captured by the water drops. So they went right through the scrubber, right through the demister. They're the stuff going out the stack, but that's what you would expect. So when we dried out the sample and removed all the water and then reweighed it, you see what happened is the water that was in this large right-hand peak went away, and we're left with this darker peak. So that dark peak that you see on the right is that dark material by itself dried out that was caught in the pre-cutter liner. You notice that essentially the shape of the left-hand submicron peak is essentially the same, because that material is the same material it was because it wasn't in a water drop. So this material told the client that they needed to get in, do some serious work on their demisters, and go ahead and repair them. So a year later, we went back. I'll point this out to you. You notice that the dark peak on the wet and dry graph is a little over 40 milligrams per dry standard cubic meter. I'll make sure I get the units right. So on the next slide, a year later after the repairs, if you go over here to 10 microns on the right, you see that small little hump. You notice it is below 10. Whereas if you go up, previously before they repaired it, it was above 40. So you can see they've reduced their carryover emissions from their scrubber by a factor of 4, a multiplier of 4, by fixing their demisters so that the drops came out. So those are the kind of things we can do with this data. It has a lot of varied applications, and in certain cases, like I said, this is dealing with particulate matter, so it has to be a solid or a liquid droplet. Now, if we're looking at plume simulation, this was a variant of when they created CARB 501. California said, what happens if it's a wet stack? Same thing everybody says, what happens if it's a wet stack? So here they used a larger pre-cutter, as you notice on the left, that took out 20, 50 micron drops, and larger, because they figured those drops are going to, when they leave the stack, they're going to rain down around in the area of the stack. They're not going to be transported kilometers in the atmosphere. And then when you quickly heat in about 18 inches, you quickly heat at 600 degrees, you evaporate, you flash off the water, release the drops from inside, and then go ahead and size the material inside the impactor. So the impactor simulates what happens if it was set up several kilometers downwind and sampling in ambient air for the plume that went ahead and dried out. So thank you. That concludes the presentation. A lot of information, but I think you can see that with the right application, you can be able to parse out quite a bit of information from a Cascade Impactor sample. Like I said, it's not widely used, but when it's used, it usually provides very, very good information that advises all the parties about the nature of what's going on in a gas stream. Thank you very much.